Hello everyone, good evening, welcome to Avalanche Breakdown YouTube channel. Next we'll discuss about GPS and GNSS. Uh, so what are the contents that we'll discuss for this video? Like we'll see what is a GPS, what is a GNSS, difference between GPS and GNSS, why GNSS is more accurate, why GPS and GNSS are important, applications in autonomous driving in robotics, GNSS Constellations, basic working principle, GNSS error sources, GNSS accuracy improvement sources, RTK GNSS in autonomous driving summary. So this document is going to be a bit long because GNSS is actually a very important sensor and there are many topics to cover. So first of all, what is GPS? GPS Global Positioning System is a satellite-based navigation system that enables users to determine their position, velocity and time (PVT) anywhere on Earth where satellite signals are available. GPS was developed by the United States Department of Defense and has become one of the most widely used navigation systems around the world. Although originally designed for military purposes, GPS is now freely available for civilian applications. GPS works by receiving radio signals transmitted by multiple satellites orbiting the Earth. By measuring the travel time of these signals, GPS receiver calculates the three-dimensional position. GPS is a global satellite navigation system developed by United States that provides accurate position, velocity and time information using a constellation of Earth orbiting satellites. Basic working principle. The GPS positioning process can be summarized as follows. GPS satellite transmits navigation signals. GPS receiver receives the signal, measures signal time travel, calculates distance to satellites, uses trilateral, computes position, velocity and time. What information does GPS provide? A GPS receiver estimates latitude, longitude, altitude, vehicle speed, heading with motion or multiple antennas, time, number of visible satellites, position and accuracy. These measurements are collectively known as position, velocity and time. Components of GPS. The GPS system consists of three major systems: space segment, control segment and user segment. What does space segment do? A constellation of satellites orbiting the Earth. Responsibilities: broadcast navigation signal, provide precise timing, broadcast satellite information, orbit information. Control segment: ground stations responsible for monitoring satellite health, updating satellite clocks, updating orbital information, maintaining system accuracy. User segment includes all GPS receivers such as smartphones, automotive navigation systems, survey equipment, agricultural machinery, drone, autonomous vehicles, robots. Advantages of GPS: worldwide coverage, free civilian service, accurate positioning, accurate timing, reliable navigation, mature technology, easy integration with robotic systems. Limitations of GPS. GPS performance degrades in environment where satellite signals are blocked or reflected. Examples include urban canyons, tunnels, indoor environment, defense forest, underground parking, heavy rain, international jamming or spoofing. Because of these limitations, autonomous vehicles rarely rely on GPS alone. What is GNSS? Next. GNSS is Global Navigation Satellite System is a general term that refers to all satellite navigation systems that provide position, velocity and time information. GPS is only one member of the GNSS family. Other global GNSS constellations include GPS, GLONASS, Galileo, Baidu. Regional systems include QZSS and Navik. Therefore, GPS is one of the navigation systems, while GNSS refers to the collection of all the satellite navigation systems. Why GNSS was developed? Originally, GPS was the only widely available satellite navigation system. As more countries developed their own satellite constellation, the need arose for a term representing all these systems collectively. Hence, the term GNSS was introduced. Basic principle: GNSS receivers simultaneously receive signals from satellites belonging to different constellations. Example: GPS satellite, GLONASS, Galileo, Baidu, QZSS. GNSS receiver will receive all the signals. The receiver processes all available signals to estimate more accurate position. Advantages of GNSS. Compared to GPS only receivers, GNSS receivers typically offer more visible satellites, improved positioning accuracy, faster position acquisition, better availability in challenging environments, improved reliability, reduced positioning errors. Modern GNSS receivers A modern receiver may simultaneously use satellites from GPS, GLONASS, Galileo, Baidu, QZSS. Using more satellites generally improves the geometric configuration and overall positioning accuracy. Difference between GPS and GNSS. Many people mistakenly use the term GPS and GNSS interchangeably. However, they are not the same. Simple explanation. Imagine transportation. Toyota is one car manufacturer. Cars include Toyota, Honda, Ford, BMW, others. Similarly, GPS is one satellite navigation system. GNSS include GPS, GLONASS, Galileo, Baidu, and regional systems. Thus, every GPS receiver is using one GNSS constellation, but not every GNSS receiver relies only on GPS. That is the difference. GPS, Global Positioning System. GNSS, Global Navigation Satellite System, meaning one satellite navigation system, collection of all navigation systems. Developed by United States, multiple countries. Coverage global. Satellites use GPS only. GPS, GLONASS, Galileo, Baidu plus others. Accuracy good, better because of more satellites. Availability lower in obstructed environments, higher due to additional constellations. Typical receiver: GPS receiver, multi GNSS receiver. Why GNSS is more accurate? Suppose a GPS only receiver can observe 7 satellites. A multi GNSS receiver may observe GPS 7 satellites, Galileo 8, Baidu 9, GLONASS 6. Total 30 satellites. With more satellites, better satellite geometry, lower positioning error, reduced signal blockage, higher reliability, improved continuity of service. Okay. Why GPS and GNSS are important? Satellite navigation systems have become essential for modern transportation. Robotics, surveying, logistics, autonomous systems. They provide the ability to determine where the vehicle is, how fast is it moving, and what time it is. All of which are critical for autonomous operation. Global positioning. GPS, GNSS enable a vehicle or robot to determine its position anywhere on Earth. Typical outputs include latitude, longitude, altitude. This forms the basis of autonomous navigation. Navigation system use GNSS data to plan routes, guide vehicles, estimate arrival time, perform turn-by-turn navigation, optimize path. Time synchronization. Every GNSS satellite contains highly accurate atomic clocks. Receivers use these signals to synchronize across systems. Applications include telecommunication, financial system, electrical power grid, autonomous vehicle, sensor synchronization. Vehicle localization. Autonomous vehicles require knowledge of their position relative to the world. GNSS provides global estimate that can be refined using IMU, LiDAR, camera, wheel encoders. Mapping. GNSS assists in HD map creation, surveying, lane mapping, geographic information system, road network mapping. Fleet management. GNSS is widely used to monitor truck, buses, delivery vehicles, ships, agricultural machinery, construction equipment. Limitation. Despite its importance, GNSS cannot provide continuous high accuracy localization in every environment. Common challenges include multipath reflections, urban canyons, tunnels, dense vegetation, indoor environments, signal blockage, atmospheric relays. For this reason, GNSS is typically fused with other sensors in autonomous systems. Application in autonomous driving and robotics. GNSS is a foundational sensor for outdoor autonomous systems because it provides global reference frame. Rather than replacing with other sensors, GNSS work alongside LiDAR, camera, IMU, radar, and wheel encoders. Global localization. GNSS provides an initial estimate of the vehicle's position on Earth. This allows the autonomous system to determine approximately where it is before more precise localization methods take over. Route planning. GNSS enables navigation software to determine the current location, select a destination, compute an optimal route, recalculate routes if necessary. Initial pose estimation. Algorithms such as LiDAR based localization require an approximate starting position. GNSS supplies this initial pose, helping localization algorithms converge more quickly and reliably. Sensor fusion. GNSS is commonly fused with IMU, LiDAR, camera, radar, wheel odometry. Sensor fusion combines the strength of each sensor to provide robust localization, especially when GNSS signals are temporary, degraded, or unavailable. Autonomous vehicles. Typical GNSS applications include highway driving, fleet tracking, geofencing, route planning, emergency assistance, HD map alignment, global localization. A GNSS constellation is a group of navigation satellites that work together to provide positioning, navigation, and time services. Each constellation is operated by a country regional organization. A modern multi-GNSS receiver can use signal from several constellations at the same time. This improves satellite availability, positioning accuracy, and reliability. GPS, United States. GPS or Global Positioning System is operated by United States. It provides global positioning, navigation, velocity, and time services for civilian and military users. GPS satellite transmit navigation signal containing satellite identification, satellite position, satellite clock information, orbital data, system status information. Common GPS frequency bands include L1, L2, L5. GPS is widely used in vehicle navigation, smartphone, aviation, marine navigation, surveying, robotics, autonomous vehicles, timing synchronization. GPS is one individual satellite navigation system constellation. GPS is one individual satellite navigation constellation within the broader GNSS family. GLONASS, it is from Russia. GLONASS stands for Global Navigation Satellite System and is operated by Russia. Like GPS, GLONASS provides global position, velocity, navigation, timing. GLONASS satellites operate in medium Earth orbit and transmit signal in several frequency bands. Historically, many GLONASS signals used slightly different carrier frequencies for different satellites. Modern signals also use code-based signal separation, similar to other GNSS systems. Advantages of including GLONASS in the receiver include more visible satellites, better availability in high altitude regions, improved satellite geometry, greater positioning continuity. Galileo, European Union. Galileo is satellite navigation system developed by the European Union. It is designed primarily as a civilian control navigation system. Galileo provides services for general navigation, high accuracy positioning, safety related applications, search and rescue, timing services. Galileo transmits signals in multiple frequency bands, allowing supported receivers to reduce atmospheric errors and improve positioning accuracy. Its major benefits include modern signal design, multi-frequency operation, high quality timing, compatibility with GPS and other constellations. Baidu, China. Baidu Navigation Satellite Systems or BDS is operated by China. Baidu provides global positioning, navigation and timing services. Its system uses a combination of different satellite orbits including medium Earth orbit, geostationary orbit, inclined geosynchronous orbit. This mixed orbit architecture can improve regional satellite visibility, particularly in Asia Pacific region. Baidu supports civil navigation, transportation, agriculture, surveying, maritime application, emergency services, autonomous systems. Modern GNSS receivers frequently combine Baidu with GPS, Galileo and GLONASS. Regional systems. Regional navigation systems provide enhanced coverage over specific geographic area. QZSS or the quasi-zenith satellite system is operated by Japan. QZSS is designed to improve satellite navigation availability in Japan and the wider Asia-Oceania region. Its orbital design allows some satellites to remain high in the sky over Japan for extended periods. This is helpful in cities with tall buildings, mountainous areas, urban canyons, locations where low elevation satellite signals are blocked. QZSS complements GPS rather than fully replacing it. It can support positioning augmentation, high accuracy correction services, timing, disaster and emergency messaging. NAVIC. NAVIC stands for Navigation with Indian Constellation and is operated by India. It was previously known as Indian Regional Navigation Satellite System. NAVIC provides regional navigation services over India surrounding regions. Applications include transportation, maritime navigation, disaster management, vehicle tracking, surveying, timing, strategic application. NAVIC is designed to provide reliable regional positioning rather than complete worldwide coverage. What is the comparison? Comparison of different GNSS constellations. GPS United States Global Navigation Timing Positioning. GLONASS Russia Global Navigation Timing Positioning. So this is basically the same. Main purpose is the same. Galileo is for European Union, Baidu is China, QZSS Japan, India. NAVIC. Benefits of multi-constellation receivers. Using multiple constellation provides more visible satellites, faster position fixing, better geometry, improved availability, better performance in cities, greater fault tolerance, improving positioning continuity. Basic working principle. GNSS determines a receiver's position by measuring signals from multiple satellites whose locations are already known. The receiver estimates its distance from each satellite and solves a set of equations to calculate its position and clock error. GNSS satellites transmit timestamp and orbit information. Receiver measures signal time travel. Pseudo range to each satellite is calculated. Multiple satellite ranges are combined. Position, velocity and time are estimated. Satellite signal transmission. Every GNSS satellite continuously transmits radio signals towards Earth. Transmitted signal generally contains satellite identification code, transmission time, satellite clock information, orbital parameters, system health information, navigation message. The receiver identifies individual satellites using unique ranging codes. These coded signals allow different satellites to transmit in the same frequency band without being confused with each other. Satellite orbit and position. To calculate receiver's position, the location of every visible satellite must be known. GNSS satellites follow predictable orbits around Earth. Their positions are calculated from navigation data transmitted in the satellite message. Two important data types are FRMS, Almanac. FRMS contains precise orbital information for a specific satellite. It is used for accurate positioning. Almanac contains approximate orbit and status information for the constellation. It helps the receiver determine which satellite should be visible, where to search for them. Approximate satellite locations. The receiver calculates each satellite's position at the moment when the signal was transmitted. Signal travel time. GNSS signal travel at approximately the speed of light, 3 × 10⁸ meter per second. The receiver compares the satellite transmitted the signal, the time the receiver detected the signal. The difference is the signal's travel time. Delta t is equal to t receive minus t transmit. Because the signals travel extremely quickly, even a small timing error can create a large distance error. For example, a timing error of 1 microsecond corresponds to approximately 300 meters. Accurate timing is therefore essential. Distance measurement. The estimated distance between the satellite and the receiver is rho is equal to c into delta t, where rho is measured distance, c is speed of light, delta t is travel time. This measured distance is called pseudo range because it contains several errors including receiver clock error, atmospheric clock error, atmospheric delay, multipath, receiver noise, orbital error. Therefore, rho is equal to true geometric distance plus measurement errors. Trilateration. Trilateration determines position using distances from known reference points. In GNSS, the satellites are the known reference point. The receiver to satellite distances are the measured ranges. A range from one satellite defines a sphere around the satellite. One satellite, the receiver could be anywhere on a sphere. Two satellites, the two spheres intersect in a circle. Three satellites, the three spheres normally intersect at two possible points. Four satellites, an additional measurement resolves the receiver's three-dimensional position and clock error. GNSS uses trilateration, not triangulation, because it is primarily based on measurement distance rather than only angles. Receiver clock error. GNSS satellites contain highly accurate atomic clocks. Ordinary GNSS receiver use less accurate electronic clocks. Their internal time is therefore not perfectly synchronized with satellite time. The receiver clock offset introduces same approximate range error into measurement from all satellites. The pseudo-range equation can be represented as rho I is equal to xi minus x whole square plus yi minus y whole square plus zi minus z whole square plus c into del t, where xi, yi, zi is equal to satellite position, xyz receiver position, c speed of light, del t receiver clock bias. The unknown receiver clock bias must be estimated together with receiver position. Why 4 satellites are required? The receiver normally has 4 unknown values x, y, z and receiver clock bias. Each satellite provides a pseudo-range equation. Therefore, at least 4 independent satellite measurements are required to solve the 4 unknowns. Satellite 1 equation 1, satellite 2 equation 2, 3 and 4. Therefore we have 4 equations and 4 variables, and 4 equation 4 variables, therefore we can solve them. With more than 4 satellites, the receiver uses an estimation method such as least square to improve the robustness and reduce the effort of measurement noise. Additional satellites can provide better accuracy, better fault detection, better satellite geometry, increased reliability. A GNSS receiver provides position, velocity and time, commonly called PVT. Position may be expressed as latitude, longitude, altitude, EC, EF coordinates, local ENU or NED coordinates. Velocity can be estimated using position changes over time, Doppler shift of satellite signals, carrier phase measurements. The GNSS Doppler measurement can provide accurate velocity even when absolute position accuracy is lower. Time. GNSS provide highly accurate time reference to the navigation system's internal time scale. GNSS time is used for sensor synchronization, communication network, power system, financial system, autonomous vehicle logging, distributed computing. GNSS error sources. GNSS positioning is affected by errors originating from satellites, the atmosphere, the receiver and the surrounding environment. The final positioning error is combination of several sources. Ionospheric delay. The ionosphere is an electrically charged atmosphere layer located above Earth. GNSS signals slow down and change phase while traveling through it. The delay depends on signal frequency, time of day, solar activity, satellite elevation angle, geographic location. Lower elevation satellite signal travel through more of the ionosphere and generally experience greater delay. Multi-frequency receiver can estimate and reduce ionospheric error by comparing measurements at different frequencies. Tropospheric delay. The troposphere is the lower part of the atmosphere. GNSS signals are delayed by dry atmospheric gases, water vapor, temperature, pressure, humidity. Unlike ionospheric delay, the tropospheric delay is not strongly frequency dependent at GNSS frequencies. It is usually estimated using atmospheric models and local weather assumptions. Multipath. Multipath occurs when GNSS signal reaches the receiver through more than one path. For example, direct satellite signal, antenna. Reflected signal, building antenna. The reflected signal travels a longer distance and arrives later than the direct signal. Multipath is common near buildings, vehicle, metal structures, bridges, wall, water surfaces. It can cause position jumps, incorrect pseudo ranges, carrier phase errors, reduce RTK performance. Satellite clock error. GNSS satellites use atomic clock, but these clocks still develop small errors because the signal travels at the speed of light. Even very small timing error can cause a noticeable range error. The control segment monitors the satellite clocks and transmit correction information in the navigation message. The residual clock errors may remain after correction. FAR miss error. FAR miss error occur when the satellite position used by the receiver differ from the satellite's true position. Since GNSS positioning depends on known satellite coordinates, orbital error directly affects the computer receiver image. FAR miss errors are reduced through ground monitoring, updated navigation messages, differential correction, precise orbit products. Receiver noise. A receiver noise originates from antenna electronics, radio frequency circuit, analog to digital conversion, tracking loops, thermal noise, software processing. Receiver quality influences. Signal tracking, pseudo range precision, carrier phase quality, weak signal performance. Survey grade receivers usually provide lower noise than low cost consumer receivers. Poor satellite geometry. Position accuracy depends not only on measurement quality but also on the geometric arrangement of visible satellites. Good geometry occurs when satellites are widely distributed across the sky. Poor geometry occurs when the satellites are clustered together, mostly in one direction, at similar elevation, visible only through a narrow opening. Geometry quality is described using dilution of precision or DOP. Common values include GDOP, PDOP, HDOP, VDOP and TDOP. Lower DOP generally indicates better geometry. Signal blockage. GNSS signals are weak when they reach Earth. They can be blocked by buildings, tunnels, mountains, dense trees, roofs, underground structures, vehicle bodies. Signal blockages reduce the number of available satellites and may prevent the receiver from computing a reliable solution. Urban canyon effects. An urban canyon is an area surrounded by tall buildings. GNSS performance degrades because direct signals are blocked, reflected signals dominate, satellite geometry becomes poor, signal availability changes rapidly, position estimates may jump between streets. Urban canyon errors can reach several meters or more, making standalone GNSS unsuitable for dependable lane level autonomous driving. Now, since there are many GNSS errors, what can we do to actually improve them? Next, differential GPS. Differential GPS or DGPS uses a reference station at a known location. The reference station receives a GNSS signal, calculates its measured position, compares it with known position, determines the measurement error, sends correction to nearby users. Because nearby receivers experience similar errors, they can apply these corrections. DGPS generally improves positioning compared with standalone GNSS, but does not normally provide centimeter level accuracy. Satellite-based augmentation systems. A satellite-based augmentation system, or SBAS, uses ground monitoring stations and geostationary satellites to broadcast correction and integrity information. SBAS can correct satellite clock errors, orbital errors, ionospheric errors. It can also provide warnings when navigation information is unreliable. Example of SBAS type services exists in different regions. SBAS is especially important in aviation and safety related navigation. Ground-based augmentation systems. A ground-based augmentation system, or GBAS, uses local ground infrastructure to provide corrections over a limited area. It is commonly associated with airports precision approach, local high integrity navigation. Because it operates locally, it can provide accurate corrections and rapid integrity monitoring within its coverage area. Real-time kinematic positioning, RTK, uses carrier phase measurements and correction information from reference station. RTK can achieve centimeter level positioning under favorable conditions. It requires a base station or reference network, a rover receiver, reliable correction communication, good satellite visibility, successful integer ambiguity resolution. RTK is widely used in surveying, autonomous vehicles, agriculture, construction, mapping, robotics. Network RTK. Network RTK uses several reference stations rather than a single base station. A central service model spatially varying errors and provides corrections to the rover. Advantages include greater coverage, reduced dependence on one base station, improved atmospheric error modeling, more consistent performance. Network RTK corrections are often delivered through mobile internet using an encrypt service. Precision point positioning. Precision point positioning, or PPP, uses precise satellite orbit and clock correction. Unlike RTK, PPP does not always require a nearby base station. PPP uses precise orbit data, precise clock data, carrier phase measurements, atmospheric modeling. Advantages: wide area operation, no nearby local base required, high long-term accuracy. Limitation: convergence may take time, performance depends on correction availability, temporal signals loss can require reconvergence. Carrier phase positioning. GNSS carrier waves have much shorter wavelengths than ranging codes. Carrier phase measurement can therefore provide much higher precision than code-based pseudo-range measurements. However, the receiver initially does not know the total number of complete carrier cycles between the satellites and the receiver. This is known as the integer ambiguity. High accurate positioning requires the ambiguity to be estimated and resolved. Carrier phase positioning is the foundation of RTK, network RTK, PPP, survey grade GNSS. Comparison of correction methods. Standalone GNSS infrastructure is none. Relative accuracy meter level. Main limitation atmospheric and environmental errors. DGPS reference station, and then sub-meter to meter level limited correction precision. SBAS regional augmentation system, improved meter level positioning, regional availability. GBAS local ground system, high local accuracy, limited coverage. RTK base station and correction link, centimeter level require continuous correction. Network RTK reference station network, centimeter level requires network service. PPP, precise global correction, decimeter to centimeter level after convergence time. Carrier phase positioning depends on method, very high precision, ambiguity resolution. Actual performance depends on the receiver, antenna, satellite visibility, correction quality, environment. RTK GNSS. What is RTK? RTK stands for real-time kinematics. GNSS is a high precision positioning method that uses carrier phase measurements and real-time correction data. RTK estimates the position of a moving receiver relative to a known reference station. A basic RTK system contains GNSS, base station, then you have a rover, and then you have a correction data. RTK is widely used when meter level positioning is insufficient. So since for autonomous driving we require centimeter level positioning, RTK GNSS is widely used. Base station. The base station is installed at a precisely known location. It receives the same GNSS signal as the rover. Because its true position is known, it can estimate errors in satellite ranges, carrier phase, satellite clock, atmospheric propagation. A base station transmits correction information to the rover. A base station may be permanently installed, temporarily surveyed, part of a reference station network. Rover. The rover is moving GNSS receiver whose position must be calculated. Examples include autonomous vehicle, survey pole, agriculture tractor, construction machine, robot, drone. The rover processes its own GNSS measurements, base station correction, satellite orbit and clock data. It then estimates a precise position. Correction data. RTK correction data is commonly transmitted using radio, cellular, Wi-Fi, internet, encrypt, satellite communication. The correction format is often based on RTCM messages. Correction data may contain reference station coordinates, code observation, carrier phase observation, satellite information, network correction. Low latency is important because old corrections reduce accuracy. Fixed and float solution. RTK float. An RTK float solution occurs when carrier phase ambiguities have not been resolved as exact integers. Characteristics: better than standalone GNSS, lower accuracy than RTK, often less stable, may occur during initialization or poor visibility. RTK fixed. An RTK fixed solution occurs when integer ambiguities have been fully resolved. Characteristics: centimeter level positioning, high confidence, greater repeatability, preferred for autonomous driving and surveying. A receiver may transition between no fix, standalone fix, RTK float, RTK fixed. RTK accuracy. Under favorable conditions, RTK can provide centimeter level horizontal accuracy, slighter lower vertical accuracy, accurate relative positioning, repeatable map alignment. Performance depends on satellite geometry, base to rover distance, correction latency, signal blockage, multipath, antenna quality, ambiguity resolution, number of frequency and constellation. RTK limitation. RTK performance can degrade because of correction link loss, tunnel entry, urban canyon, multipath, long distance from the base station, poor satellite geometry, antenna obstruction, cycle slips, insufficient initialization time. RTK alone does not guarantee continuous centimeter level localization. Autonomous vehicles normally fuse it with IMU, wheel odometry, LiDAR or camera localization. Means even with the help of RTK, what happens is we get centimeter level accuracy, but the problem is like sometimes there are cases wherein we don't get GNSS signals. At that time we cannot wholly rely on RTK data. That's why we also depend on LiDAR, IMU or camera data so that we can localize in a better way. Next, GNSS in autonomous driving. GNSS provides a global positional reference for autonomous vehicles. Its role is especially important for route level navigation and initialization. But it is usually not used as the only localization source. Global localization. GNSS provides a vehicle's approximate position on Earth. This allows the autonomous driving system to determine which road is it on, which map region to load, its approximate position in the road, whether it is inside the intended operational area. Global localization is different from local localization, which estimates the precise vehicle pose relative to nearby map features. Initial pose estimation. LiDAR or camera based localization often requires an approximate initial pose. GNSS can provide approximate XY position, altitude, heading when available, position uncertainty. This initial estimate helps map matching algorithms such as NDT or visual localization coverage to correct the location. Route planning. Route planning uses a vehicle's current global position and destination. GNSS helps the system select the starting route, calculate the route, monitor route progress, detect route deviation, recalculate the route. The route planner generally uses road map data rather than the raw GNSS coordinates alone. Map alignment. HD map uses a geometric or projected coordinate reference. GNSS measurements must be transformed into same map coordinate system. Map alignment may include datum conversion, latitude and longitudinal conversion, local map origin definition, altitude correction, heading alignment. Incorrect map alignment can place the vehicle beside actual road or in the long range. Lane level positioning. Standard standalone GNSS is usually not accurate enough for dependable lane level positioning. Lane level localization often requires RTK GNSS, multi-frequency GNSS, IMU fusion, LiDAR map matching, camera lane localization, wheel odometry. Even centimeter level RTK can fail temporarily in tunnels or dense cities. So redundant localization remain necessary. Vehicle testing. GNSS is used extensively during autonomous vehicle testing. Applications include recording ground route trajectories, measuring test route coverage, comparing planned and actual path, evaluating localization error, recording vehicle speed, synchronizing sensor data. Repeating test scenarios. Survey grade GNSS INS systems are often used as reference system during validation. So now we have almost completed the complete document, and let's see the summary. Global Navigation Satellite System (GNSS) is the general term used for satellite-based systems that provide position, velocity, time information. GPS is one GNSS constellation, while other systems include GLONASS, Galileo, Baidu, QZSS, and Navig. GNSS works by receiving radio signals from multiple satellites whose orbital positions are known. The receiver measures the signal travel time and estimates its distance from each satellite. Using measurements from at least 4 satellites, it calculates 3-dimensional position and receiver clock through trilateration. GNSS position may be represented using latitude, longitude, and altitude, or converted into coordinate systems such as ECEF, ENU, and NED. WG8S4 is the most commonly used global reference system for GPS coordinates. Positioning accuracy is affected by ionospheric and tropospheric delays, satellite clock, and orbital errors. Receiver noise, poor satellite geometry, signal blockage, multipath, and urban canyon effects. Multipath and non-line of sight signals are especially significant in cities. Accuracy can be improved using methods such as DGPS, SPAS, GPAS, RTK, Network RTK, PPP, and carrier-based positioning. RTK uses correction data from a known base station or reference network and can provide centimeter level accuracy when satellite visibility and communication conditions are good. In autonomous driving, GNSS supports global localization, initial pose estimation, route planning, HD map alignment, lane level positioning, geofencing, vehicle testing, and sensor synchronization. However, GNSS is not sufficiently reliable as a standalone localization source, particularly in tunnels, urban areas, and regions with signal blockage. For robust vehicle localization, GNSS is commonly fused with IMU, wheel odometry, LiDAR localization, camera localization, radar odometry. Important GNSS performance parameters include position accuracy, velocity accuracy, heading accuracy, update rate, time to first fix, satellite count, type fix, availability, and integrity. The main conclusion is that GNSS provides the essential global reference for autonomous vehicles and robotics, while other sensors provide the local precision, continuity, and redundancy required for safe operations. So I think with this we have come to the end of this document. This was a very long document. So in this document we have seen what is GPS, what is GNSS, difference between GPS and GNSS, why GNSS is more accurate, why GPS and GNSS are important, applications in autonomous driving and robotics, GNSS constellation, basic working principle, GNSS error sources, GNSS accuracy improvement source, RTK GNSS in autonomous driving, and summary. With this I would like to end this video. Thank you.